Hi everyone. Hello Fabio. Hello Alex. Today I am presenting my presentation dedicated for dissertation, Machine Theory of Mind. Hope you enjoy. I will cover the main idea and concept of theory of mind in machines. I will explain the need and motivation behind. Then I will go through several possible theory of mind implementations. At the end I will focus on one specific implementation that I will use as a base for my dissertation. So motivation. First, let's talk what is theory of mind. Basically, it's a field in psychology that studies the ability to address the mental states of other individuals. In general, theory of mind describes the modeling of the mind for better understanding of a person. Practically, it helps explain the behavior of observed agent, so the observer and observed agent could cooperate more efficiently with a deeper understanding of each other. The main issue of theory of mind is that observer doesn't have direct access to the mental states of somebody other, so it must rely on some secondary signals like facial emotions, voice features, behavior, etc. For example, by observing that the person cries and observing that his finger is cut, we can make a prediction of feelings that he feels pain without direct access to emotions. And which is important, the observer can predict next actions based on that mental states. Like if a person suffers from pain and it has a pain relief near, there's a high probability it will take that pain relief, right? How to identify the theory of mind abilities? The best known way to prove that an individual has theory of mind abilities is by passing a false belief test, like ToMnet-N test. The idea of a test lies in the principle of separating the own knowledge and the knowledge that another agent could have. It considers situations where the agent may work in not optimal way from the objective point of view, while according to the limited knowledge of the agent, it is the best optimal behavior. It will be shown clearly in the video later. ToMnet-N test shows that an observer can realize that an agent might have false beliefs about the world. It could be wrong about knowing, it could be wrong without even knowing it is wrong. That could be resulted in non-optimal behavior of an agent which is considered as optimal with false beliefs. So, why machines need theory of mind? The main features machine could get from theory of mind abilities are understanding of agents' desires and preferences, and predictions of actions. Using both of these points, machine can achieve higher efficiency and safety while working in the environment with other people or other machines. Please look at the implementation of a theory of mind for drones that is presented by Anca Dragan, a researcher from Microsoft Research Group from Romania.
So here's an overhead view on the right. We have the human and the quad rotor. They each have their goal. And what you'll see is the robot making predictions about what will happen at the next steps. There's some low probability or high probability. And now the quad rotor uses that to make sure it's not in the way. Here's another example. Person for that goal. This is not perfect, right? Because people are noisy when they're actually walking through the. Like we get this perfect data, but we can make predictions about what's going to happen.
So we saw the action predictions that helped cooperate together, avoiding collisions. However, predictions of action is not a novelty and there are many other methods to achieve that, but please look at the next case where probably all existed methods would fail without having a theory of mind abilities.
And so here's an example you actually saw in the beginning. What we did here is we spilled some coffee on the floor. Now Sylvia is avoiding the coffee. The robot models Sylvia as noisy rational. The robot has no idea that there's coffee on the floor, that humans care about avoiding coffee that's spilled on the floor. And so Sylvia is kind of deviating, but the robot very stubbornly believes at every point that Sylvia will turn around and start going straight toward her goal.
The motivation of developing theory of mind for machines is quite wide. There are many possible applications. The supportive surgical robots would predict which tools the doctor would need in the next few seconds. The autonomous car could predict that the child may cross the road to get an ice cream on the other side. The chatbots would be more realistic, with a deeper understanding of the feelings of the person they speak with. So let's talk about implementations. There are a lot of possible solutions, and I'll go briefly through them. BDI. There is a model of belief, desire, intentions. It states that individuals observe the environment, which results in forming some beliefs of or knowledge about the world. Then these beliefs influence the desire to change something in the environment. Afterwards, desire leads to intention to satisfy the desire. So an engine prepares a set of possible plans of actions to do so. And finally, observation of the environment helps in choosing the best plan to achieve the desired goal in the current circumstances. However, the model is very realistic and based on human reasoning. Most of implementations don't have learning, and beliefs are hard-coded, as well as desires, which make the approach unusable for the goal of the dissertation. IRL. Currently there are many applications of IRL in the fields close to theory of mind. You can see some of them shown on the left above the header. Talking about the main principle, it's next. Rational agents usually want to reach their goal with the least cost. The mental reasoning could be expressed as reinforcement learning agent, and therefore we could apply inverse reinforcement learning to get some mentalizing about the agent. The reinforcement learning agent learns the policy function that maps the environmental states to certain actions, and an agent can do this according to the given reward function. Invert reinforcement learning set the problem in another way. You are giving some observations of policy and you see which actions an agent takes. According to observations, inverse reinforcement learning tries to build a reward function which could be interpreted as some kind of mental states, some kind of preferences, desires. However, it's not easy to extract information from it, from the reward function. The building of reward function can significantly help to predict actions. And the last one is the neural networks. There is a beautiful approach. So I found a model that could be one of the leading in the field among other neural networks. The model ToMnet is created by DeepMind 4 years ago. It was applied to a grid world game 11 by 11, where it had to predict where an agent would go, which colored square it would consume, which trajectory it will use, and etc. just from observation of past trajectories. You can see that the architecture consists of 3 neural networks. Character and the mental nets return or output some embedded spaces, HR and eMental. They create some clusters, and these clusters can give highly interpretable information on mental states. I made a separate presentation exactly on ToMnet. The link is on the slide. You're free to go to see the more details on that mentalizing and clustering the mental states. So here you can see how ToMnet passes false belief test when the consumable objects are changed outside of sight of the agent. ToMnet still predicts that an agent will go to pick a blue object which it prefers because it remembers it was up, which is a false after a swap of the objects. So the model can separate its own knowledge from the agent's knowledge, as it has a full observability of the and is aware of a swap, while agent has limited observability and it is not aware. And ToMnet can understand that and can predict actions with a high accuracy, but unfortunately the code for ToMnet wasn't found. But I found publicly available code for ToMnet implementation, which is an extension of architecture. It's ToMnet Plus. I'm going to study the code and the paper on this extension. I will try to find limitation, for example, lack of scalability and a lack of optimization of architecture. It's simple and straightforward. and I'm going to fill that gap by the end of my dissertation. Thank you.